Go ahead. I don't need it right now. It's okay. Okay. You want to take pictures of it? That's fine. Okay.
My heart procedures are not going to be done this week. The hospital, I'm going to be hospitalized next week. So my intention is to write the exam this week. And so we will definitely have exam 2 next week. And whether I administer it or whether someone else administers for me, we'll have to choose a day. So either Wednesday or Friday. With that, there'll be a heavy emphasis on quantum, which means being able to solve multidimensional quantum systems, being able to solve one-dimensional particles in a box, being able to do harmonic oscillators, be able to do separation of variables, be able to do hydrogen atoms, be able to work with associated Legendre polynomials, be able to work with recursion, example. So that's the area where we will be hitting it heavy, so make sure you know it all. Exam probably similar to what it was last time, 2.5 to 3 hours. Expected, you'll be given a formula sheet, and I would expect, although I haven't actually worked it out yet, that you'll probably be given a math handbook for intervals, since you obviously will have to do a lot. Other than that, nothing else. Close notes, close books, get a formula sheet, that's it. All right, moving on where we were from last time. Oh, by the way, I guess the one other thing, I have done most of your homework problems, so I expect that I'll have those back in the new assignment out to you this afternoon. I finished a good portion of them at my mother's dinner table late at night down in Clear Lake. So, fortunately, I think I have the approximation problem left. I think it was problem number 4. That's the only one I have left to grade. When we left, we talked about spin and we talked about magnetic fields. And so now I want to go one step further and talk about total angular momentum. So I have multiple momentum. I have a momentum due to the fact that we can think of it as the electron orbiting the nucleus. And then we have this intrinsic angular momentum, or spin, that you can think of as a ball spinning. But don't go too far with that, because you can get yourself in trouble. All right, so you can't calculate the speed it spins, and it isn't really spinning in regular space. It's a 4th dimension, a new type of dimension. So for us, we'll leave it kind of thinking about it, but I warned you that because you're going to take more advanced classes where that'll get you in trouble. So you get these 2 vectors. These 2 vectors don't have to align. And furthermore, if they interact, which they will, because we talked about if you have spin, that's like a magnet. And from the electron's perspective, you can think about the proton going around it and having this magnetic moment. And those 2 magnets are going to interact between them. And because they interact, it turns out that neither the orbital angular momentum nor the spin orbital angular momentum is conserved in transitions. But the total of the 2 is. So that leads us, when you deal with spin-orbit coupling problems like the book talks about, which hopefully you read, then they want to talk about the total angular momentum rather than the individual. So the total angular momentum given its own symbol J, and it is a vector like all angular momentums are. So because it's a vector, it has to add vectorially the orbital angular momentum and the spin angular momentum. Now, you may remember when you were adding all these vectors with little arrows and everything back in Physics 1, beat up on you with those things, and we broke them into components and all this. But you got a little problem here about adding components. You can know the z component, for instance, of one of these and the total length, but you can't know the x and y, so how are you going to add them up? Turns out it's not as bad as you might think. I think that's really kind of evil and it'll be really difficult. Turns out it's actually really true. Because we're going to work with the quantum numbers rather than with the vectors themselves, but it's the same. So if you thought of this like here, where there's some sort of L, remember that L is actually somewhere in a cone. I'm not going to draw the cone because of my drawing skills. So this thing has this somewhere in the XY. I just know that it's on a cone. And then there's also the spin. But the spin might be pointing like that. So there's some spin. And those two produce some J. And you can't know the X and Y component of the J either. So you can think of this spinning and that spinning somewhere. And then of all of those uncertainties is this J, which is also in a cone. And there's a lot of pictures of those cones and graphics. I'm going to try to do them. If you look back in iceberg and resin. The question is, how do I get J? And how do I get the quantum numbers to go along with J? Because the J is going to have a little j for a quantum number. It's going to have an m sub j to represent how much is on the z component, because it's an angular momentum, and all angular momentums obey the same math rules. And it turns out that is not so hard. So the best way probably to do it is to do an example. So let's take a 2p electron. What are the possible values? For the electrons total angular momentum. By that I mean the magnitude. Okay. So I want to find J. But I'm told this. So, for a solution, actually turns out not to be that hard. In fact, although the book does it obviously correctly, I think a graphical picture is a lot more useful than just the numerical stuff he does. It's a p electron. What does that tell you?
L equals 3.
Huh?
L equals 3?
No, L
Only
does
2.
not equal 3.
2.
L equals something but A3.
Right.
Huh?
It's 2.
It's not 2. It's 1. So keep going. That would be really bad to miss that question.
I'm flipping P and D.
That would be really bad because I tell you what, it's going to be that's going to be one of the easiest things you get on the test.
So it's
And S is 0, L, E is 1, E is 2, F is 3, N is 2 in this problem, L is 1. I also know something else. I know S is 1/2. That's guaranteed because it's an electron. So I know both quantum numbers. Yeah.
Couldn't it be negative 1/2?
No. The negative is the M part of it, the M sub S, whether it's up or down. This is the one related to its length. Its length is always 1/2.
Yeah.
The M sub S is 1. Because this is always the same, people don't usually write it down, but it's still true. What people usually write is they'll write the L, the N, the M, L, and the M sub S. And that's fine as long as those are not talking. But when you start talking about total, you start talking about true spin coupling effects, then L, the angular momentum is not conserved, and S isn't conserved, so those aren't good quantities because they don't stay constant in the problem. You want to choose things that don't change. The energy level doesn't change, and it turns out the L, okay, the J will not change, and you can know the M sub J. That's what I want to get. Now, I need to add these guys. Think of these guys as arrows, but one-dimensional arrows. All right? So we're going to put L. It doesn't matter which one do. We're going to put L. So here's L. It's got a length of 1. And now I want to go along and I want to add S. The S-var can either point up or you can point down. That's it. So one possibility is I make the S like this, and it's about half as long as the other one. If I can draw that right. And then to find J, the quantum number, your requirement is that you add those two arrows together. And how long should the arrow be? 1.5. That's it. So one possibility is J equals 3/2. That's when the spin and the L are aligned. Now they're not perfectly aligned. They're going to be tilted. But if you were to add up all the tilts, the net length, what you would have to get is this quantum number to get you that right length. That's a hell of a lot easier to think of three-dimensional arrows. All right? So one possibility is you add the quantum numbers, just like they were vectors, but you add them aligned. Now, there's another possibility. You draw L. And this time the S isn't aligned, it is in the opposite direction. So, I wanted to draw the other one, sorry. So think of it like you walk into camp. You started here, you walked up 1 unit, you walked back half a unit, so how far did you really go up? 1/2. Now, for each of these is an M sub j, which isn't actually asked for in our problem, but would be true. So for this problem, M sub j could be from minus j to j, differing by 1. So the possible values would be M sub j equal minus 1/2 and M sub j equal 1/2. Two states. This one, you go from minus 3/2, and you'd add 1, so you go to minus 1/2, then you'd add 1, you go to 1/2, then add 1, you go to 3/2. 4 states. 4 plus 2 is 6 states. The same number you had in the uncoupled representation. Number of states didn't change, but they have different magnetic effects. Now once you got the J's, it's easy to get the total angular momentum. All you got to do is use the formula for angular momentums. The angular momentum's magnitude is h bar times the square root of its quantum number times its quantum number plus 1. That's true for all angular momentums. The only thing you needed was the J's. And if you can add arrows, you can get the J's. So you just plug them in. So J equal 1/2. The magnitude of the total angular momentum is h bar times the square root of 1/2 times 3/2. That's the square root of 3 over 2 h bar. So that's one value you might measure. The other value that you might measure occurs when this is 3/2. Then you get the square root of 3/2 times 5/2. You get the square root of 15 over 2 h bar. If I do that right. So those are the angular momentum values you can get. This one, when the S and the L are aligned. That one, when the S and the L are not aligned, it can be in either state. Now in spectroscopy, what people will do is they don't write the spin. They tell you the L, they tell you the N, and they tell you the J that they got. So for instance, if you were in this state here, there would be 2 states of these. One for MJ equal minus 1/2, one for MJ equal to 1/2, and these 2 states would be called the 2p 1/2 states. That's by N, that's by L, that's by J. There'd be 2 states. And one electron could occupy each of those states. Only one. We'll come back and talk about that in a minute. There are never more than one electron in any state. Never. And there's another set of states over here. Mj equal minus 3 halves, Mj equal minus 1/2, Mj equal 1/2, Mj equal 3/2. These are the 2p 3/2 states. And there are 4 of those. So when people give you this type of spectroscopy, in essence, they've told you both which direction the S is pointing. They've told you the L, and they've also told you the N. These states will not be at the same energy just because of the internal magnetic field that exists in the atom. So in the book, in chapter 9, if you were reading the examples and things that he did, so he has the 1/2 states down here in the lower energy because of the interaction between the spin-orbit coupling between the magnetic field and the spin. And he has this one has been shifted upwards. This is due to the internal B field. This is not if you put an external field and split them again. This is just due to the inside of the atom. So the electrons would want to fill up the lower states first, and then the upper states. You want to fill up the lowest energy possible. So even though you may think that the principal quantum number says they're the same energy, they're not going to be exactly the same energy because of these spline effects. This explains why the periodic table does what it does. However, look at the shift here versus this gap. That's not on the scale. It'll be much bigger. Much, much bigger. So the principal orbit still dominates the big effect. These were known as spine splitting lines. So very small shifts in the lines. If you didn't look very closely, they looked like one line. But if you look closely, you saw they were distinct. They were distinct because of this splitting. And we can explain that. Also know the number of states and electrons. You we have 2 and 4. That's always true that they end up even. They don't end up odd like they do in orbital angular momentum. So you'll get 4, 2. You never get like 5 or 3. They're always even. This is something else that comes out of this physics. Now, what he does, and it's totally correct, is he just writes the math equations rather than drawing the little arrows. So if you look at this in my arrow picture, if I can put my arrow picture over the top of it, if these 2 arrows are, I'm not quite have one of them. If those 2 arrows are aligned, you get 3 halves. Well, you get that just by putting 1 plus a half in here. And if they're not aligned, you get the minimum value, which would be L minus. Yes, absolutely. So it would be 1 minus a half. Now, it seems like this is a waste because you only get 2 answers. That's assuming, for instance, that S is a half. There are particles in isospin and nuclear physics and elsewhere that you're not limited to just a half. You can have 7 halves, you can have 5 halves, you can have other values. And if you do that, for instance, if you added 3 halves and you subtracted 3 halves, you get much broader range of values. All right? And so the key thing is that they still have to differ by 1. They always have to differ by 1, just like L had to differ by 1. So addition and subtraction, they're either fully aligned close to being fully aligned as you can, or fully unaligned, and these can be thought of partially aligned. And that's how you get the numbers. I always found it just easier to draw the arrows and get to know all the answers. Right? I also don't forget the name formulas when I draw the arrows if I don't do them for a while. But it's exactly the same. This math is those arrows. And in fact, in advanced nuclear classes, there's a thing called Bornheim rules, broad nuclei and such. You can either do it that way, or you can just do it with the arrows. You get the exact same results either way. And I never can remember all the Nordheim rules that occur, so I did these here. Probably can memorize them if I did them once, rather than once every 10 years or what have you. That's too bad. But I'm not a nuclear theorist. All right, leaving that section, I'll talk about some other things. I sent you a couple of problems. These are easy problems because they're mostly very little modern. They're mostly freshman stuff. So it makes it easy to pick up some points. These things have rotational energy because they have angular momentum. Then if you quit thinking about atoms for a minute and start thinking like molecules, then those molecules are described by quantum numbers, and they should have wave functions, just like the angular wave functions, the spherical harmonics. And you should be able to find energies for them, and you can. And when you do that, although some people will write L, it's generally written as J that you're talking about. And the energy can be described for a problem like the following. Carbon monoxide molecule with a bond length. Okay, so it told me a link between the two atoms. So you're looking at something kind of like C, there's O, and think of it as a rod between the two. And you can think of it that this thing can rotate around that rod, just like two balls with a rod between it, and it can have energy. Now, classically, it can have any rotational speed it wants. That means it can have any angular momentum it wants. But quantum mechanically, that's not possible. It only can have certain angular momentum values, and therefore only certain energies. And those energies, therefore, give changes because it can absorb a photon and change its spin, or its angular momentum, or it could emit a photon, for instance, and change. So we want to look at those. So I remind you of a couple of things about this. And I did send you these problems. The energy, we're just talking about kinetic here. So if this was translational, how do you write kinetic energy translationally?
P squared over 2m.
I'm sorry?
Is it P squared over 2m?
P squared over 2m. And now the big board. P is linear momentum, so what do I replace it with? Angular momentum. So it becomes L, or if you prefer total angular momentum, it becomes J. This one's kind of an orbital. I'll just leave it that way. So L squared instead of P squared. And then I have 2. And then M is the mass, which is a measure of inertia. But in rotation, we replace inertia with? I, rotational inertia. All right, that's the big stuff we have to have. By the way, something else you want to remember. P is equal to, how do you find linear momentum in physics? Freshman class.
Mass velocity.
Mass times velocity. So, okay, so instead of P, I'm going to replace an angular by L. And instead of mass, which is a measure of inertia, I'm going to replace it by moment of inertia, I. And instead of velocity, I'm going to replace it with omega angular velocity. So if you knew L and you knew I could ask you to calculate the rotational speed of the molecule. In fact, they will. The fact it's not in your book is not relevant because you're supposed to pass physics 1 and 2, so it's fair game. And likewise, if I give you the rotational speed, I could ask you the angular momentum. And people do. They do it in your textbook. And he's not going to go back over that. Okay? Now, that's a rigid body formula, but it's true in this problem. So both of these you have to bring from physics 1. So you want to put in here. What comes in from modern is you can replace L now, because we have a formula for it. So all that's new in this problem is that L is h bar square root of L times L plus 1. So if you square that, it's h bar squared L times L plus 1.
It's equal to L. Oh, wait, no, E.
It's the quantum number. And if you were doing J, which would be probably a more general statement, then you would make that J times J plus 1. So there's a set of levels, okay? So 0 means it isn't rotated. It has no energy of rotation. That's not a rotational state. We don't generally deal with that. L equal 1. All right, so if you had L equal 1, you get 1 times 1 plus 1 is 2. And so you have 2 h bar squared over 2I. And if you made L equal 2, then you get 2 times 2 plus 1 is 3. So you get 6 h bar squared over 2I. Now look at this. This guy here, this is 0. That's h bar squared, right? Over I. And this, that's 3 h bar squared over I. 6 divided by 2. So that's 3, and this was 1. So these guys start going up. You can sit there and figure out they're going to go off a very systematic set of things. And if you think about this as kind of the first one, then this guy, so call that the first level, the lowest level. Then this guy right there, he's 3 times that low. And I'm not going to go through filling this thing out. I'll let you sit down and you should be able to do simple algebra and fill it out yourself. But if you were to take 3, you get 3 and 4, that'd be 12. So 3 and 4, that'd be 12. And 12 divided by 2 would be 6. So you go up, and you keep doing this on and on and on. Okay? So I'll leave that for you to do. Play around and look and see, make sure that you understand how these guys differ and how they're the same. Okay? And how the spacing varies compared to the hydrogen atom and compared to the harmonic oscillator and compared to the particle box. I could give you a bunch of energy diagrams and ask you to tell me what was the type of system that it had without telling you the system and asking you to find the energy levels. Make sure you can work backwards, because that's what we really do. We measure energies, and then we work backwards and figure out what caused those energies. We don't get problems where they give us, set up the little model and determine. You read what nature says, and then we have to figure out what in nature and outer space, wherever it's causing them. That's the way real world problems are. They're not the way textbook problems are. They're the inverse of textbook problems. So make sure you practice that. We'll not do that to you on this exam. Final game is fair game, which basically means I'm going to do it to you. All right, if you haven't figured that out by now. So, with that formula, I should be able to calculate anything you want to know between this and this. And that's the only part of this section that's anything new for modern physics. First one says, calculate the moment of inertia of a Cl molecule. Well, I have a problem because they're rotating about the center mass. Either I have to find the center mass and deal with two moving objects, or I should do what you do in classical mechanics, which is smartly replace this with the same length here, whatever that r is, and a new mass, u, a reduced mass, just like we did with the Bohr atom. So I, what is the moment of inertia of a point particle from physics 1?
Mass times length.
It's not mass times length, but you're close. Mass times length squared. Mr squared is 1/2 mr squared for a cylinder. It's mr squared per a hoop. It's 2/5 mr squared per sphere. You should know this by now. If you don't, you're behind every other student. All right? Those are things that were in Physics 1. You're supposed to know them. You will need them in statics and dynamics. You will need them on the national test. They're FE testable things. If you miss on the FE, you're not getting to go to get the IE thing. Make sure you don't forget these things. So the difference here is that that's mu, r squared, rather than m. To find mu, you multiply the two masses and divide by the sum, which we already did this semester. Usually in physics problems, unlike engineering problems, the masses are usually about the same size, whatever they are. In this case, they're 10 to the minus 26 kilograms. So you could write, y'all probably would, write all that, multiply that, divide by the sum. That's a waste of time. All you really need is 1.99 times 2.66 over 1.99 plus 2.66. And then the whole thing is times 10 to the minus 26 kilograms. What that enables me to do is make a rough check. That's about 2.5, and that's about 2. This is a little bigger than 5. And this thing down here, I'm sorry, so 2 times 2.5, that's about 5, and this thing down here, that's about 2, and 2.6 something, so that's about 4.5. This thing's a little bigger than 1. It's also got to be smaller than either of these numbers. This is the same sort of formula you get for resistors in parallel. So it's smaller than either of the individual. So it's between, we know it's less than 1.99. It's closer to 1. If these have been exactly 2, each of them, it would have in fact been 1 exactly. So you'll need a calculator at that point, but you know it's somewhere in about, 1.3, 1.4, something like that. And I did that, I punched my calculator, and I got 1.14. So I got that. So now I can calculate the moment of inertia. 1.14 by 10 to the minus 26 kilograms, very small thing. And then I was told the length was 1.13 times 10 to the minus 10 meters squared. That was given to me right up here. So they said R is that, 0.113 meters. You square those two together, and you get about 1.46 by 10 to the minus 46 kilogram meter squared. Extremely small. I don't think you're measuring that. So unlike a classical problem, like in engineering where you might measure the mass of 2 balls and the length of the rod, you're not going to be able to do that with any precision. Furthermore, these things are actually held together and then move around due to invisible rods. So you can even find the rough you want. What you'd really do is not do the way this problem is written. This problem's written like a textbook problem. You would get the final answer at the end, you get the energy from the measurement, and you'd work backwards and you determine the bond length. That's how they know how these things are bounded. You measure the energy, that you can measure because you measure photons, and then you work backwards to find the bond length. Rather than the way they make it, which is like a freshman physics problem. You have these two masses that go around, you measure, you know the bond length, how the hell do you get in there and measure that? It's following the wavelength of light. And then you calculate what the energy should be. They actually work the other way. Yeah.
I have a question.
Yeah.
It's nothing related to this, but you see how mu equals that stuff? How mu equals M1, M2.
Yeah.
How is that related? When I took circuit theory?
No. I can show you how to do it, but it's going to take time. It's in my notes previously.
Okay.
What it does is that you're rotating around the center of mass, which isn't moving. So
Okay.
you calculate the distance from here to here and there to there for the center mass.
Oh.
Then you calculate the energy from that. Well, I don't want to do that problem. I want to get the same energy from a single point with the same R, but with a new mass. So by equating those two, that's how you do it.
Okay.
It's actually in the notes. If you go back to 4-atom and hydrogen spectrometry.
Okay.
If you have trouble with it, come see me and I'll walk you through it.
Okay.
But it's about 6 or 7 line proof. It's not hard, it's just algebraic and time consuming. You spend 15 minutes or so. Now, if you have that, we already said we knew how to find the big board, then we got life pretty good. It says lowest non-zero rotational state. That means L equal what? 1. So my thing says that E is equal to H bar squared 1 times 1 plus 1 over 2I. And I just got I. So let's see, that's H squared. Now you may know H bar, but I don't know H bar off my head. Times 2 pi squared times 2 times I times 2 on the top. Well, that's nice. I just cancel this 2. So H is 6.63 times 10 to the minus 34 joule seconds. That I know off my head. Mr. Lowe made me memorize that in high school. This is 4, this is pi squared. And I have above 1.46 10 to the minus 46 kilogram meter squared. Now obviously, if it's been given some other set of units, then I wouldn't have had to use that. I could have used my HC or something. But in this case, everything's in SI. So you're not really saving anything by not doing SI. See, that's very small. You're going to square that, it's going to be minus 68. That's about a 46. So you get 68 minus 46 is about 22. So 10 to the minus 22 joules type, roughly. So this isn't even an EV. These are in like micro electron volts. And you'll need to punch a calculator to do all that. If you do that, you come up with 7.63 by 10 to the minus 23 joules. And if you, of course, convert that into electron volts, you get 477 micro electron volts. So half a milli electron volt, if you will. And the last one, which is completely a textbook-oriented problem, but it's where I stole it from, so why not? Actually, I stole it off the test, but I stole it from the textbook before that. It says calculate the angular speed, and you got a couple of choices. One would be work from L. The other one is to say, hey, but isn't this just 1/2 I omega squared? So omega would be the square root of 2e over I. And if you do that, so it spins really fast. Again, you can't measure that. You can measure this. From that, you can work backwards. You can find a bond length for that molecule. And then you'll know that for every other problem that you ever may have to work. Well, you know you didn't miss it. Well, if you have lots of different experiments and they all require that bond length, then no matter how you measure them, you better get the same bond length every time. So physics isn't about knowing one answer to a problem. You can make up any old theory to get one answer. It's the fact that as you do more and more problems in physics, so you have this one set of data that this pin represents that you have to get. But then you have this other experiment, and it gives you exactly the same answer. Now you get 2 pins. And then you get 3, and then you get more, 4. The strength of the physics and its ability to predict is because of the strength of the bond of the group. You can make up anything to explain gravity. I can have the, repulsive ground theory. But whatever I do, without making any changes, it must explain all experiments. Not just one experiment. This isn't social science. And that combination makes it incredibly powerful. With just a few things, we can explain the universe. These things can be used to spectroscopy in outer space and astronomy, and they are. You can get spin flipping with hydrogen, and we have. In fact, you shoot radiation in this particular millimeter radio. I used to know what it was, 1.2, 1.12. Remember, millimeter, and you shoot this radiation into outer space. And they found that, weird, it would send it back. It must be alien life. It wasn't alien life. What you're doing is flipping the proton into higher energy state because you shot it through a gas cloud of hydrogen. And a little while later, the proton wants to go to the lower energy state, so it falls back down and emits the radiation back. And it just matches the same way. It's not intelligent at all. Okay? Just because you get something back from something you shoot at does not imply it's intelligent. But people thought at the time, and a lot of people still do, that they're intelligent life out there because of that. So, this is a good problem in that it doesn't require much physics from this class, but if you didn't master your last stuff, it gets you. Another one, similar type of problem in the book we don't spend much time on. This one, again, matches up with the data from the last one. So we still have the same bond length and everything, but now we've got a set of masses, same as before, but we assume that the molecule is now absorbing a line at a particular frequency and it's due to vibration. So what do we have now? Well, this time we have a physics problem like this. And we have the reduced mass on the spring. So I'll remind you a few things about that. Omega is the square root of K over mu. F is the number of cycles. Omega is the number of radians per second. Okay? So 2 pi radians per cycle. And that's the relation between those two variables. So put that together and I have this. So let's see, 4 pi squared F squared is K over mu. Or is omega squared. So if you told me this, it says it has a particular absorption line frequency, then I can actually work through this and find K. And there's no modern physics actually in that whatsoever. If you want to make the problem a little bit more modern, you could tell me the energy that it absorbs. If you told me the energy it absorbs, let's say this is the n equals 0. So the energy is h bar omega over 2. This is the n equal 1, 3 h bar omega over 2, and so forth. Then that delta E is h bar omega. So if you gave me the energy, I can divide by h bar and I'd have the omega, then I'm back into physics 1 again. You're not allowed to forget anything in your career. Your senior year will expect everything. Your boss will extend everything plus your lifetime thing. He will not expect you to know the rhyme of the Ancient Mariner by Samuel Taylor Coleridge, or to remember, simple lines out of Shakespeare, for instance, in Hamlet, Don't expect that, to be or not to be. That is the question. Whether there's noble in mind, suffer slings and arrows of outrageous fortune, or take arms against the sea of trouble, and by opposing to end them. Although you should know these things. You went to school, didn't you? They will not ask you that. But if you think they're going to ask you your paper stuff, you're nuts. And they just say, look it up. Expect you to be able to call it on demand. And the only way you do that is you study enough that you put them in places in your brain for long-term retention. If you crash study and if you look things up, you will not, and therefore you are not advancing. Make sure you are putting in the necessary time. If you're not, you're basically staying in Little League. but you're trying to compete against high school and then eventually pros. And they're not going to be sympathetic. All right? It's not a hard thing. It's not about being brilliant. It's not about being super smart. It's about doing the right things in every course, every time. It's about seeing the connections between courses. You can't do that if you don't put the time in. You can get by and skip by for a year or two. But eventually they'll come up and bite you. A students become B students, become C students, become, hopefully graduate, but don't go on. B and C students eventually don't become students. They get to be out and go do something else. Put the time in. I'll take hard work over brilliance any day of the week. Unless you were just a super prodigy, and I hadn't seen any of you guys solve calculus at age 6, like Weisskopf, then you can't rely on that. Right? There are lots of smart people in the world. Been around a long time. These problems are simple and easy, fair game. Probably a whole lot easier to do those hydrogen wave functions. So you would not want to miss one of these problems. Make sure you can handle vibrations and rotations inside the textbook. And that's all we're going to say on them. We'll leave them and go on. Pauli exclusion principle. Oh, we have time. Just a few minutes. The Pauli exclusion principle makes an interesting statement. And you can argue that it can be understood just purely because it explains the fact of chemistry. But that's not where it came from. It says for two fermions, these are any particle that has an odd half integer spin. No two can occupy the same state. Another way of saying that is no two can have the same set of quantum numbers. Now if they're a boson, they have an integer spin, they can't. This was a Nobel Prize winning idea. It explains everything about the periodic table. Yeah.
With the bosons, earlier we were talking about fermions because they have the half spins.
Yes.
When you do spectral analysis, you always get the 4 spots.
Yeah.
What can you do that with bosons? And if you can, what
You
you
can
get?
shoot
What you
bosons through, and you can think of bosons beyond the idea of just particles and think of nuclei, for instance.
Yeah.
So, for instance, if you have a helium-4 nuclei, and you have 2 protons and 2 neutrons, no matter how you add those up, you're going to end up with an integer spin. You can end up with 2, you can end up with 1, you can end up with 0, but you get spin. So that's a boson.
So would you get 5 spots?
Yeah, you get more spots,
5 in it.
depending on what state it's in.
Yeah.
Now what happens with these guys, though, is that they like each other and they'll condense at low temperature, and you get this condensate that has really unique properties. Another, if you have helium-3, which has 1 less neutron, it behaves totally differently, because it's a fermion. And then you get fermion condensates, and there's a whole different set of physics involved in that. So these guys become very important as you go on further on up. Right now, we're just caring about electrons. But I tell you, it's a universal statement. It's not just here. And people will assume again that you know it from the past class. Now, where does all this come from? Well, your book tries to show you about a bunch of math, and I can do that too. But it comes from the idea of indistinguishable particles. So I'm going to greatly simplify, and obviously this isn't really totally true, but let's say you had a helium nuclei. So you had 2 protons and 2 neutrons here. And there's 2 electrons, and we will lie to you. There's one of the electrons. He's well-defined classically. And here's another electron over here, which I'm going to draw in a different color. There's electron 1 and electron 2. They're different states, different orbits, if you would. Okay? Well, there's potential energy because of this distance, call that R1. And this guy has a particular potential energy because he's out here at R2. And they both have kinetic energy because they're going around. So if I was to write that out, I would have minus, and then I would have p squared over 2n, right? But it's not a one-dimensional problem. So the first one, he has some set of your partial derivatives. But those derivatives are dependent upon his value of x, y, and z, or in this case, r, theta, and phi. So I put that thing to say, well, that is the derivatives, but they're derivatives based on his coordinates. And then you'll have some potential energy. And that potential energy would be minus K, and there would be 2 protons, so it would be 2e times an E. And it would be over his distance. And all that would get applied to the wave function. And that'd be related to that particle. But the wave function must depend on more than this. The wave function must in fact depend upon this guy's position over here because it's the whole atom. So for that electron, there must be an equivalent statement. There must be potential energy, and there must be, kinetic energy, and there must be potential. So it also has to depend upon I lost my squares there. So if you add all those together, if you put both of these together, because obviously they're all in one atom, then you're going to have a sum of energies, the energy of that electron, the energy of that electron, the total energy. And there are parts of terms that depend on the position of the second electron, goes to the first electron, potential of the first, the potential of the second. Now, I've left out something. What I've left out is that electron has a force on that electron. We're ignoring that for the moment. All right? Book and elsewhere. Hopefully, this is the dominant. Those are called interaction terms, and they make the problem considerably harder. So we're going to leave those out for a minute. But if each one of these guys is involved in this, and each one of these terms, when I add it all up, sum these two together, really, count for both electrons being in the atom, then what I'm talking about is each term only depends on one electron's coordinates. So that means it's separable. And if it's separable, that means this guy could be written like this. It could be written as the state of the first guy and the state of the second guy. So if you solve the hydrogen atom or something equivalent for the 2 protons here, you can take the solution for the red electron and multiply by the solution of the green electron, or the brown electron, and get the total. Now here's the thing. If I didn't color code those, couldn't I switch those electrons and not change anything? Obviously don't change the energy because they're all identical electrons. That means these are degenerate states. That'd be like me switching the R1 to R2. So the Pauli switch crystallization kind of comes from the fact that you can switch those coordinates. From the fact you don't measure the side, you measure the square of the probability. That leaves us 2 possibilities, even and odd. That's where this guy comes up. I'll see you guys next time.